Good evening, all. So, welcome to the week 3 live interaction session for this course Waste to Energy Conversion. So, as usual, let's just wait for a minute or so before we begin our session for today. So, I think we can start. So, before starting, I would like to uh, convey that it is my apologies for not conducting the live interaction session last Sunday. Actually, there was internet disruption, and the way it happened was the internet disruption started at around 4:50 p.m. So I tried to connect through multiple sources, but unfortunately, none of them worked, and that internet issue continued till 6:30 or 6:45. So after that there was no meaning for conducting the live interaction session. So then I approached the NPTEL team asking what could be the possible solution so that I can cover up on the week 3. So thankfully they understood the situation and they extended a offer to conduct this live interaction session on any other weekdays. So this slot was something which was more comfortable for me, and I believe 6 p.m. to 8 p.m. would have also been a comfortable slot for most of you, since majority of you may be working or you may be from you or you may be studying. So I think this slot was much perfect for everyone, so I booked this slot, and thanks for them for understanding the situation, and apologies to all of you for not able to communicate to you uh, during that session. I mean, in case if any one of you were waiting for quite a long time. So, without any further delay, let's start our session for today. So, let me just share my screen. So, I hope my screen is visible. So, let's start our session. So, I welcome you all to the week 3 live interaction session for the course Waste to Energy Conversion. This course is offered by Professor Prasenjit Mondal sir from the Department of Chemical Engineering IIT Roorkee under the NPTEL SWAYAM program. Myself Pratyumnan, a PhD student from the Department of Chemical Engineering IIT Guwahati, Assam. I conduct live interaction session for this course in this particular Jan to May 2026 semester. So we have completed two lectures or 2 weeks content on waste to energy conversion, and we have also seen both in the course as well as the live interaction session on the basics of this particular course and what we are interested in learning from this course. So we discussed about starting from the very basic definition of waste, then we progressed towards characterizing the waste and understanding the different types of waste material that is available. So with that particular information, we kind of categorized the waste to energy conversion process in three different ways. I hope all of you are familiar by now the three different ways. The first one is the thermal conversion, second one is the chemical, and the third one is the biological conversion routes. So our week 2 live interaction session was something where we focused on thermal conversion route, and in the thermal conversion route we are having three different process. First one is combustion, second is gasification, and third one is pyrolysis. So last live interaction session we concentrated on incineration, or also you can call it as combustion. This week we will dedicate our interest on gasification and the syngas utilization of that gets produced through the gasification process. So I hope all of you are able to differentiate between the three different types of thermal conversion routes that we discussed earlier. So what is the fundamental difference that separate each of these conversion routes from one another? Anyone quickly? How is each process different from one another in terms of a particular parameter which differentiates each of them? So it is nothing but it is the value of R in the sense the ratio between the oxygen to the biomass feed that you are feeding it into the system as fuel. So based on that we classify the thermal conversion routes. So I hope all of you are very familiar with this table. We discussed this even in the last live interaction session. So how does the O2 to coal? So here it is coal, but but as such in general it means oxygen to that of the fuel or the biomass ratio. So as we discussed in the last live interaction session also, based on this value we differentiate the conversion process, the thermal conversion process. So if your value of R is going to be greater than 2.5, then it's a combustion process. If the value of R is defined between 0.68 to 2.5, it is a gasification process. And if your value of R is going to be less than 0.68, then that process is going to be pyrolysis process. So typically we reduce as we progress through the conversion routes. We can identify that we are trying to reduce the oxygen requirement gradually. So initially we had excess of air. When I mean excess of air, I meant excess in comparison to its stoichiometric ratio. So in that excess of air, we call that process as combustion process. And when we had a ratio wherein it is between zero point 0.6 to 2.5, which is typically something you can say is a controlled fashion for oxygen flow, then we call that process as gasification. And when we do the conversion process of waste materials under limited supply of oxygen, or you can also say limited supply of air, that particular process we term it as pyrolysis. So I hope there is not much confusion related to this. So this table we will be using even in our next live interaction session where we will discuss about pyrolysis. So this table is going to remain constant as we go through the course. So if you see in case of the coal gasification and the biomass gasification, which happens in a controlled oxygen environment, both the processes are very similar. So usually the parameters that defines all these processes are usually similar for both of them. However, only the nature of the feedstock basically determines whether the biomass basically determines the difference in coal gasification and biomass gasification. So if you see, it totally depends upon the nature of the feedstock that defines the process. So if you see, coal is actually a very less reactive material. So that since it's a very less reactive material, the energy requirement for that process is going to be different compared to the biomass, which is going to be a very high reactive material in nature. So that is how I said that the nature of the feedstock is the one that is the difference which creates a difference between coal gasification and biomass gasification. So once you take a biomass or any kind of, let's say, carbon based feedstock, and then if you are going to heat them, or let's say burn them, then burn them in a controlled oxygen environment, or you can say when you gasify them, you are going to obtain some amount of, something as a product, or you can also say some combustible gases are going to be generated as product, and that is what you can see here. So since in case of the combustion or incineration process you use excess supply of air, often you do not end up with CO and H2, unlike what you see in case of gasification, because there you are trying to do that process under controlled atmosphere. Whereas if you see that in the case of pyrolysis, since very less amount of oxygen is used, chances of forming H2 and CO2 is very less. Predominantly that composition of the pyrolysis process, what is going to be produced, will have carbon in the form of solids, or what you actually call as char. Then you will have carbon monoxide and hydrogen gas. So if you see in case of gasification, you are going to end up with the carbon monoxide, hydrogen gas, water vapor or water in the form of steam, and carbon dioxide. So this carbon monoxide plus hydrogen forms what you call it as a syngas. Syngas is also known as synthetic gas. Am I right? Okay, any synthesis gas, yes, exactly. So wanted syngas is known as synthesis gas. So let me write that here. Syngas or synthesis gas. Now this is in case if you have oxygen environment, the entire somehow you are able to provide an environment in such a way that only oxygen is there for is there in the surroundings for the burning. But let's say for example you do not have that facility, or you do not have that ability to only purge oxygen into the reactor, whereas you purge air into that reactor, then what you will end up with? So you will end up with a high concentration of nitrogen. So apart from carbon monoxide and hydrogen gas, you are also going to have nitrogen gas within the system, so that you call it as a producer gas. So since nitrogen gas is unreactive, it cannot react, so whatever the amount of nitrogen gas that enters within the system will remain as such. But it will decrease the yield of CO2 and H2 that gets produced within the system, as oxygen concentration is less. Now here comes a question. So basically the use of this synthesis gas is used for multiple purpose, but one among the many purposes is for energy production. Now I have something so called as syngas, and I also something called as a producer gas. Now so making of, so between these two, which one will be more useful for the utilization process, or which one will be more beneficial for energy production process? Is it the producer gas, or is it going to be the synthesis gas? Among these two gases, so instead of maintaining an oxygen only environment or a pure oxygen environment, if I'm going to use air for gasification process, I'm going to end up with producer gas. So among these two gases, which one will be beneficial for energy production, or you can say power generation, or energy generation? Anyone? Which among the two is useful for energy generation or for utilization process as such? Syngas. Okay, there are many responses which say synthesis gas or syngas as the answer. Now the question is why? I mean, why you prefer synthesis gas over producer gas for energy generation purpose? High energy density. Yes, so nitrogen is typically going to be inert, so that will not contribute to your heating or adding to that of your heating value. So the amount of energy that gets, so the amount of heating value that the material carries with them in case of the syngas will be more. So as such, it will be able to generate high energy density compared to nitrogen gas what is produced if air is used for the production of synthesis gas, or you can say producer gas. So now, typically, these concentration of the, or you can say the composition of the product, as I said, even in case of the producer gas, these concentrations are typically going to vary depending upon your R values. So, for example, if I take the value of R as, let's say in case of gasification itself, we have this R value in terms of a wide range, right? 0.68 to 2.5 is quite larger values for consideration. So you can have, so depending upon the type of, or depending upon the value of R that you have, or depending upon the value of, or depending upon the type of product that you require, you can actually tune the value of R. So if you say, for example, let's say that I do not want to keep, like I do not want more amount of carbon dioxide or steam getting generated through the gasification process. Then in that case, what you can do is you can actually take the value of R or supply very less amount of oxygen compared to your biomass feed to the gasifier. And same thing goes if in case if you do not want more amount of CO and H2 to be produced within your system. So then you can actually go for high values of R. And that similar thing goes even with the pyrolysis process. So if your R value is going to be, let's say, 0.68, the amount of carbon char that is going to get generated will be low compared to the amount of char that gets generated if your value is, let's say, zero point 0.5 or 0.34. I hope that is clear. So by tuning the value of R, you can play with the relative concentrations of the products that are generated out of the three different processes. Is that fine with everyone? Any questions for so far? Anyone? No. Okay, so let me continue. So based on this, so what we typically obtain through this gasification process is a syngas. Now, what are the uses of this syngas? So before let us okay before discussing on the uses of syngas, let's talk about how this gasification process is happening within the system. So typically for this gasification process to happen, we use something so called as a gasifier. Like how you do in case of incineration, how we discussed about the different types of reactors. I hope everybody is able to remember great firing. So please try to recollect all those things, because that same type of same type of what do you say reactors are the ones which we will be using in case of the gasification process also. So gasifiers are typically used for the gasification process. They are the reactors in which this gasification process is conducted. So based on that, you have totally three different types of gasifiers. One is your fixed bed, second one is your fluidized bed, and third one is your entrained bed gasifiers. So in case of fixed bed gasifier, okay. So in case of bed gasifiers, you have two different types. Fixed bed gasifiers. You have two different types. One is the anyone who wants to let me know which one is the what are the two types of fixed bed gasifiers? A and B. Yes, anyone? Two types of fixed bed gasifiers. First one is the updraft, and second one is the downdraft. So what is the difference between the updraft and the downdraft gasifier in terms of arrangement of the systems, or you can say in terms of their operation? That would be better in terms of their operations. So updraft gasifier predominantly uses counter current flow mechanism, whereas downdraft uses concurrent flow. Am I right or wrong? Yes, no, anyone? Updraft, in case of updraft, there is counter current flow of the oxygen or air and the biomass feed. And in case of a downdraft, you have a concurrent flow. Is it fine or is it direction of area? So in case of the updraft gasifiers, the major mechanism is the air, or you can say the oxygen, is purged inside the reactor from the bottom, and the biomass or the feed is fed from the top of the gasifiers. So there is a counter current flow of the oxygen or air and the biomass feed. Whereas in case of the downdraft gasifiers, the feed is same. The direction of the feed is same. The feed is fed to the reactor from the top. However, in case of purging the reactor with air or oxygen from the bottom, you do that process from the sides of the reactor. So, due to which So there are typical advantages of doing that particular process. But before that, let's see about the updraft gasifiers. So in case of a fixed bed gasifier as such, the particle size that you use to do the gasification process is going to be high. Your feedstock particle size is going to be high. It is typically going to be in the order of 2 to 50 micrometers. So when you are having to have such a large feed particles, what actually happens is, and when they both of them are going to be in the counter current direction, bigger the particle size, so they will be more dense, so they will tend to come to the bottom of the gasifier much faster. Where and So what happens is, since they tend to come to the bottom of the gasifier at a much larger rate compared to how much air is getting purged through the column, what happens is the contact time for the particle and the oxygen together, that contact time of the feedstock particle with the air gets reduced. So the gasification process is not efficient enough in case of the updraft gasifier. So in case of the combustion zone, if you see, a gasifier is splitted up based on the type of reactions that happens in the gasifier. You can actually split the gasifier into four different regions. Starting from the top is drying, then you have pyrolysis, reduction and oxidation. So majority of the gasification reaction happens in the midsection of your gasifier. So since these particles are heavy and they are going to settle at the bottom very fast, the amount of time that is available for the gas and the particle to undergo reaction or to come in contact with each other is reduced. So efficiency of the process is reduced. So much amount of the feedstock particle is not going to be converted to the form of combustible gases, what we want from a gasification process. So these particles tend to deposit on the surface of the reactor. So over the period of time, as this process keeps happening, dead volumes of this feedstock gets accumulated on the walls as well as inside the reactor, which basically blocks the airflow, and it typically blocks the airflow, and it blocks the channel. It results in the channeling of the reactor, and that decreases the efficiency of the process. Overall efficiency of the process is decreased in that way. So due to this, the updraft gasifier, the outlet gas temperature, or whatever the temperature that you get out of this updraft gasifier, is only in the order of 250 degrees Celsius. So that is 4 times less compared to what temperature is maintained inside the updraft gasifier. So the amount of energy that you can actually extract from this updraft gasifier is very less. So in order to counteract, they use downdraft gasifiers. So this is where the idea is. So the thing is, we know that at the midsection or the combustion zone, the particle time is actually reduced. That is the problem. So instead of using the air from the bottom, what about if you directly purge the air at the midsection itself? So if you do that, the thought process is that we will be able to purge more gas, and more amount of the particles will come in contact with the air, and the combustion process will be efficient, so that we can get the um, syngas with or we can get the combustible gases with a greater energy, so the efficiency of the process can be increased overall. So this is the basic principle behind updraft and downdraft gasifier. I hope the things were clear. If you have any doubts, please let me know. It's simple. It's basically the direction of oxygen and the biomass speed. Since in case of updraft gasifier, contact time between the feed and the oxygen is going to be less, instead of purging the air from the bottom, you purge the air from the midsection of the gasifier, so that contact time can be increased to improve the efficiency of the process. So that is the thing. So let me just write that here quickly. I'm going to use the word unburnt. So quality and quantity of syngas is reduced. Syngas temperature is low. Unburnt feedstock leads to blocking and channeling of reactors. So this blocking and channeling of reactors, there can be a thought, why can't we just go inside, why can't reactors can be clean to remove the scales and the deposits that gets generated out of this unburnt feedstock. But we have to keep in mind that these gasifiers are going to be very long systems, and cleaning and channeling of them requires a complete shutdown of their operations, and then it has to be clean, and such process is very time consuming, and commercially speaking such process is very you can say infeasible. So of course fixed bed gasifiers are being used, but it has many limitations. So in case of downdraft gasifiers, this problems are reduced. However, there is another problem. The problem is basically the scaling up of the gasifier is difficult in this downdraft gasifiers. So overall, the thing is the temperature that is basically required in case of the fixed bed gasifier is going to be very high, 1500 to 1800 degrees Celsius. So this is where we actually go for a fluidized bed gasifier, which requires much less temperature compared to the fixed bed gasifiers. If you remember, even in the combustion or the incineration process that we studied last in the last session, we also discussed even over there about the fluidized bed and the fixed bed. I hope all of you are able to remember. So in case of fluidized bed gasifier also, we classified them into two different types. So anyone, here it will be three, but anyone who knows the two different types of fluidized bed gasifier? Yes, we did this last week. Two different types of fluidized bed gasifier. It typically depends upon the velocity of the airflow. Circulating, yes. And another one. First one is circulating, and then there is another one. It is bubbling fluidized bed. So in case of this bubbling fluidized, so again, here you also have the third, which is nothing but it is the dual fluidized bed reactor. So before moving on towards dual fluidized bed reactor, we as I said before, The bubbling and the circulating fluidized bed reactor typically differs in the velocity of the air that is flowing inside, so both of them usually use sand media, and the air is basically passed inside the fluidized bed gasifiers, which basically causes the sand particles to move. And once you feed the reactor with the biomass, the feed particles and the sand particles are going to meet, or are going to come in contact with each other. And these sand particles, and you also provide temperature, so that is basically causes for the heat transfer, which results in the burning of the particles, and the gasification process takes place, resulting in the combustible gases. Now in this, which one has higher velocity, in which case higher velocity of air is used? Is it in the bubbling fluidized bed or circulating fluidized bed? Where is the velocity of the air that is purged within the system, or purged inside to the gasifier, is more? Is it in the circulating or is it in the bubbling fluidized bed reactor? This also we saw in the last live interaction session, as well as in the course. May not be something what we typical what is exactly stated in this week's course content, but the primary difference was discussed earlier in week 2. Circulating fluidized bed has a higher velocity of air compared to the bubbling fluidized bed reactor. So I hope if there are any chemical engineers or chemical engineering students, then they will probably know about this fluidized bed reactor. Just in case if there are anyone from any other majors or from any other branches, then I would encourage all of you to actually go through this fluidized bed. So, depending upon the velocity of the air that is used, the fluidization process is categorized into multiple different regimes. So, among those is one is fluid bubbling, and another one is the circulating fluidized bed. So, the major advantage, okay, what is the major advantage of a fluidized bed gasifier in comparison to the fixed bed gasifier? This we discussed in the last session. Okay, let me just give a kind of a hint. So, in case of a fixed bed, temperature or operating temperature is between 1500 to 1800 degrees Celsius. However, in case of a fluidized bed gasifier, you can reduce the temperature, operating temperature you can maintain the operating temperature between 900 to 1100 or 1100 degrees Celsius. So, you can reduce the temperature of operation for a fluidized bed gasifier compared to a fixed bed gasifier. So based on this, I hope you are able to understand, I hope you are able to answer which one of them is ideal for use, or why is fluidized bed gasifier operates at a lower temperature compared to a fixed bed gasifier. Yes, anyone? Oh, we had answers, I'm sorry. Oh, okay, no. So anyone who knows the difference? I mean, who knows why fluidized bed gasifiers are operated at low temperature? So kindly have a look at it. I will state the reason. So it is typically because in case of the fluidized bed, the rate of heat transfer is comparatively high. Are you guys able to recollect? Someone has stated. Solid has to act as a liquid, as a fluid. So yes, that is one reason, and because of that only the rate of heat transfer is more in case of a fluidized bed compared to a fixed bed gasifier. So since the rate of heat transfer is more, the amount of temperature that is required to attain, or that is required to drive particular reactions, is very less. So that is the reason operating temperature of a fluidized bed gasifier is in the range of 900 to 1100 degrees Celsius. And as I hope all of you can correlate, an increase in the temperature demands for the increase in the amount of fuel that is required to produce the temperature. So it's not just a temperature intensive process, it also becomes as a energy intensive process. So fixed bed gasifiers is an energy intensive process, which again, as more amount of energy is needed to produce that particular amount of temperature, that directly correlates with the cost to produce that energy. So commercially speaking, if you compare fluidized bed and fixed bed gasifiers only in terms of their operating temperature, then fixed bed gasifiers are more beneficial compared to the, sorry, fluidized bed gasifiers are more beneficial compared to that of your fixed bed gasifier. So in case of the fluidized bed, you also have something called dual fluidized bed. Here the only difference compared to the normal fluidized bed gasifier, that is your circulating or the bubbling, it is just that the combustor, or where the process of oxidation, reduction and pyrolysis takes place, uh, I mean, you have totally two different chambers. One is your combustor and the other one is your gasifiers. So it's just that instead of doing both the process inside one gasifier, you actually split them into two. Now, apart from this fixed bed and fluidized bed, you have also a third type of gasifier, which is called as an entrained bed gasifiers. So the basic reason why I am going putting more emphasis on that is basically because this fixed bed fluidized bed concept is not just something that is only for this kind of combustion or gasification. These fixed bed fluidized bed reactors are used for a lot of different purposes in case of the chemical engineering industries and also in other different types of industries. So knowing their basic principle, their advantages and disadvantages will be useful. So that is the typical reason why I try to take up this again and again, rather than just stating as a fixed bed and a fluidized bed gasifier. So yes, then third one is the entrained bed gasifiers. Anyone who knows the what is the typical working principle of an entry bed gasifiers, other than stating that all the biomass and the feed are fed into the system from the top, and then you get high quality syngas. What is the operating principle or working mechanism for an entrained bed gasifiers? Anyone? Or you can also say how is fixed bed, fluidized bed, and entrained bed are different from one another. Fixed bed, I hope you will know. Fluidized bed, you can identify the difference between these two. But how is entrained bed gasified different from fluidized and fixed bed? So please have a look at them. Difference between all the gasifiers. Difference in working principles. So please have a look at it. That's the reason I'm highlighting it with the different colors. So please. So this is about gasifiers. Now I know what is a gasification process. I know how it is basically used. Now let's come to a most important part, that is how what are the products that are going to come out of the gasification, which is nothing but it's just syngas. And now how I am going to use my syngas for variety of purposes or for different purposes. So syngas is used for variety of purposes. So among them, a few of them you can say are, so the very first pro, use of syngas or synthesis gas, you can say first is in for it is used for hydrogen production. This is the first use. Apart from that, it is used for the syngas as such can be used to run a gas turbine, and from there you can do electricity production or energy generation, electricity generation. And this syngas, depending upon the temperature, you can also use them to convert water into steam, and then that steam can be used to run a steam turbine, which also leads to electricity generation. After this comes the something called as chemical production. So this synthesis gas or syngas can also be used to generate a variety of chemical products. So one is the methanol and derivatives. Typically speaking, liquid fuels. So methanol and its derivatives. And another thing is it is used in the Fischer-Tropper synthesis process. Tropper Fischer-Tropper, sorry, process. I hope there is some spelling error. Okay. So, so these are the wide variety uses of synthesis gas, or you can say the syngas. So, again, each one of them have their own way or process of dealing that we will take up as we go through the the problem solving session. So in case if you have any doubts so far as what we have discussed, you are welcome to ask me now before we progress towards our problem solving. Anyone with any questions? So we are concentrating on every week on particular thermal conversion routes. So in the last week we stopped at incineration, or you can say combustion. This week is for gasification. Next week or week 4 we will dedicate more on pyrolysis process. So with that we come to an end on thermal conversion. So probably the live interaction session that we will have on Sunday, we will close with thermal conversion routes, hopefully. Anyone with anything that has to be discussed in gasification process? Okay. So in case if you have nothing to discuss, let's move on to the problem, or you can say the multi-choice questions. So, which of the following solvent, the first question is which of the following solvent is used in the select sol based absorption process. The first option is methyl diethanolamine. Second is dimethyl ethers of polyethylene glycol, DEPG. And third one is methanol. Which of the following solvent is used in the select sol based absorption process? Now, before moving on to this, let me know for what particular purpose do we use this select sol as a solvent? I mean, why this particular question is being asked here? Or it is in relation to what? What are we trying to uh, absorb using these solvents? Or what are we trying to do here? Why do we need to go for all these absorption processes? What's the answer for the first question? Option B. Okay, but on which context is the discussion of this absorption process? And any other answers? I mean, one of you have told that uh, dimethyl ethers of polyethylene glycol DEPG is used in the Selexol based absorption process. Is that correct? And again, the question was on why we are using this absorption process. So the answer for this is DEPG. Yes, that is correct. It is basically used for syngas cleaning. Is that right? Oh, okay, I mean, now if it is for syngas cleaning, what are the kind of gases these solvents are going to absorb? Anyone? Okay, let's talk about that as we go forward. So, in case of this Selexol based absorption process, what kind of an absorption it is? Is it physical or is it chemical? Yes. So somebody has told that we are going to absorb CO2 and sulfur compounds. As such, when it is termed as sulfur compound, we mean H2S, dihydrogen sulfide. So yes, we are going to do CO2 in H2S absorption for syngas cleaning. And what is this? What type of absorption process is it? Is it physical or is it chemical? No, I'm not asking for question two. We are still in question one. So this DPG, which is used as a solvent in the Selexol-based absorption process. So this absorption process is physical absorption or chemical absorption. This is physical absorption process. So similarly, now tell me what about in case of methyl diethanol amine and methanol, whether they are physical absorption or chemical absorption process, or as you can say it's for question 2 also, MDEA, methyl diethanol amine, is used for physical absorption or chemical absorption or both A and B. Somebody, I think they, that's what they mean, that is MDA is used for chemical absorption. So does everyone agree with that? Okay, B. Okay, so MDA is chemical absorption, or or methyl diethanol amine basically use chemical absorption to absorb H2S and carbon dioxide. Okay, so we know for dimethyl ethers it is physical absorption. For MDA it is chemical absorption. What about for methanol? All these are there within the slides. Syngas utilization 1, the title is. But we need to recollect all those things so that it will be beneficial not just for solving the assignment but also in your final exam that you will give probably within a month or so. I don't know the exact date, but I think probably within a month. I think probably it will be in March if I'm not wrong. So what about methanol? Is it physical absorption or chemical absorption? So methanol will be physical absorption. So once you do this, what you are going to do? Okay, you are going to basically remove CO2 and H2S from the syngas. Then what will happen to the H2S and CO? Again, these three different processes basically absorb H2S and CO2 in different levels. But before discussing on that, let's discuss about what is going to happen to that CO2 in H2S. Okay, CO2 you can let it in the atmosphere, carbon dioxide, but what about the H2S? Can you leave that hydrogen dihydrogen sulfide just like that, or do you need to post process, do some sort of a post process treatment um, before its exhaust? What will happen to H2S? Fate of H2S. So typically you will go for a desulfurization process, right? So you will try to extract sulfur from the H2S. So typically the reaction, I will write it here. So zinc oxide will react with the H2S and it will give zinc sulfide plus H2O. Now, just a second. Now, this zinc sulfide, will react with oxygen to back give back zinc oxide plus sulfur dioxide. So, this is the total desulfurization process. So what is the second reaction called? What do you do? The zinc sulfide is basically heated in the presence of oxygen to give zinc oxide plus sulfur dioxide. What is this process? What process is this called? Okay, let me make it more clear. 1.5 O2. Okay, then it will be more balanced. Burning a sulfide in excess of air or excess of oxygen. It has a typical process in metallurgy. It's called roasting. I think I received an answer. Yeah, roasting process. Whereas if the same thing, I mean, you cannot do it for sulfide, but if you take a carbonate ore and if you try to use limited supply of oxygen to recover or to generate carbon dioxide, then that process is called calcination. So have a note of it. So once you get sulfur dioxide, you basically go for a sulfur recovery process. You basically try to react this SO2 with H2O to form sulfuric acid, or you go for something so called as a direct sulfur recovery process, or you go for something so called as a Claus process as well. So this is about the syngas cleaning and how do you remove the sulfur from the syngas. So, before moving on to that question, I told that each of these process or each of these absorption or each of these solvents that are used in the absorption process absorb different amounts of H2S and CO2. So, anyone with that particular data, or shall I write that? So, this absorbs around 98 to 99 percentage of H2S and CO2 somewhere less than 30%. Whereas in case of your Selexol based absorption process using dimethyl ethers of polyethylene glycol, you absorb around 99 percentage of H2S. However, the absorption of CO2 varies, it's a variable. Whereas in case of your methanol absorption process, the amount of H2S that you are going to absorb is between 99.5% to 99.8%, and CO2 will be around 98.5%. Again, these values are there in the slides, so kindly have a look at it in the week 3 course content. So in case if there are any figures are wrong, then kindly apologize for the same, and please have a look at the course slide for the values to reconfirm. So this is about the syngas cleaning. So I hope I have covered the process, and if you have any doubts, you are welcome to ask me. Before we move on to question number 3, again that is also, it's a straightforward question. You are supposed to know what is the particle size and the moisture content in the entrained bed gasifier system. So question 3, anyone, and anyone with the doubts in question 1 and 2. I typically want to go through almost all the options, because sometimes in the exams you may end up with, as far as my experience is concerned, you may end up with the multi select questions also. So where you are supposed to select more than one correct options. So it is better to evaluate all the options. I mean, not for all the questions, but at least for few of them, where you can actually discuss, so that you have clarity related to all the options which is being discussed. Question number 3, anyone? Oh, we have an answer. Option C. Is that right? Anyone in the audience who can let me know whether this option is right or whether this answer is correct? So everyone fine with the option C? Particle size is less than 1 millimeter and the moisture content is 15%. For those who do not, who are kind of facing whether they know or not, kindly have a look look in the slides for the values, because this is option C. Okay, so this is a data which is there in the slide, so please have a look at it. Now let's go on towards our next question. Let's go with question 6 first before moving to oh, sorry, just a second, there is a mistake. So let's go with question 5 before moving towards question 6 and 4. So this is also one of the ways to utilize a synthesis gas. As I said, syngas can also be utilized to form methanol, CH3OH. So now the question is, methanol synthesis from carbon oxides, or you can say CO, and hydrogen happens in the presence of which of the following catalysts? Copper and zinc oxide, copper and silicon oxide, iron and zinc oxide. So apart from telling the answer, please let me know what exact catalyst is used. What is the answer? Oh, we have an answer. Oh, okay. Methanol synthesis from syngas. CO plus H2 gives CO plus H2 is called synthesis gas. From there, you try to derive methanol. And what is the or which catalyst is used for this particular process? Before that, I hope all of you are aware of what is the use of a catalyst. A, enhance the rate of reaction. Option A, okay. Somebody says option A. Yes. So catalyst is basically used to speed up the reaction by decreasing their activation energy barrier. So a particular reactant is trying to form a product. So in this process, it has to undergo a what exactly word we can use. So it has to react with each other, and then it has to basically form an intermediate and then later form a product. So for this, it basically requires certain amount of energy called as an activation energy. So if your activation energy is going to be very high, then it will be difficult for the product to be formed. Catalyst basically decreases this activation energy barrier and helps in the formation of the product, and that is the purpose of a catalyst. For this particular question, it is copper and zinc oxide, but let me know the exact catalyst that is used in the methanol synthesis process from CO and H2, CO plus H2. Is it just only copper and zinc, or does it also involve some other oxides? And apart from this, are there any other catalyst that is used? So it is a combination of copper oxide, zinc oxide, and aluminium oxide, or you can also say this as alumina Al2O3. So it's a combination of all the three oxides which is used in the methanol synthesis process. Apart from that, you also have oxides like mixture of chromium and zinc oxide, and you have zirconium based oxides. So have a look at it. You have a list of the different types of catalysts that is used in the process. Now, what are the reaction that is involved in this methanol synthesis process? Okay, it is CO plus H2 is going to react to form CH3OH in the presence of copper, zinc, and copper oxide, zinc oxide, and alumina. So apart from that, are there what are the typical sets of reaction that happens in this methanol synthesis process? Have a look at those reactions as well. Now we basically go towards our next question. For low temperature methanol synthesis process, which of the following process is used? For low temperature methanol synthesis, which process is used? Is it methyl formate formation method or is it the BNL method? Anyone answer for this? For low temperature methanol synthesis, which process is used? Is it methyl formate formation method or is it BNL method or is it none of the above two? A, okay, only one. I mean, two of them has told methyl formamate formation method. Then what about BNL method? That is not used for low temperature methanol synthesis. MEOH is methanol, so instead of writing methyl or CH3OH, it is MEOH. Me is methyl. What about BNL method? Oh, what is the full form of BNL? I mean, it is Brookhaven National Laboratory Method. Probably that is the place where this reaction was first demonstrated. So that's the reason it is named after that lab. So it is BNL, Brookhaven National Laboratory. So, as per few of you in the audience, methyl formamate formation method is a low temperature methanol synthesis process. What about BNL? Is it high temperature methanol synthesis or does it require relatively more temperature compared to methyl formamate formation method? Low temperature. Can I say both are correct answers? Both your formate formation method and your BNL method are right, are the correct, both of them are correct. Is it fine or no? Or you have some reservations against these? Is it right or is it, I mean, wrong? Like, can't I have two options as correct? I would say both the options are correct. So this was actually a multi-select question. So sometimes you may actually encounter questions wherein out of four options, two or three of them may be right. So only for that particular purpose, this question was intentionally made into it was intentionally made in such a way that two options are correct here. So both of them are correct. The first one, the methyl formamide formation method, as well as the Brookhaven National Laboratory method for the low temperature methanol synthesis. Both the options are absolutely correct. So this is just for a practice wherein you may end up in places where you have to select more than one correct. So that is the only purpose of having this question. So let's move on towards the next one. Again, please have a look at each of this method and their particulars. Like, what is the Brookhaven National Laboratory method? Like, it typically employs nickel catalyst with triethyl glycol dimethyl ether. So all those formation steps as well as the reaction. So try to have a kind of an idea on what are these, so it may be useful. Okay, let's skip this slide for today because that is more on pyrolysis. uh, yes, let's go to question 11. SNG primarily stands for supernatural gas, substitute natural gas, and specific natural gas. Let's not do this slide today because this has more questions on pyrolysis process. So I'll this content will you will be able to see on Sunday. That is our week 4 live interaction session as well. So let's focus on question 11 and 12. What is an SNG? The full form. I mean, SNG is an abbreviation. Its full form is asked in this question. So what does SNG stands for? It is. So any ideas before I B? Okay. It is called substitute natural gas, or you can also say it as a synthetic natural gas. So please have a look at these abbreviations in case if any of you are not aware of that. So next, class process is used. Now we discussed this few minutes before. Class process is used for A, recovery of elemental sulfur. B is recovery of nickel, and the next option is recovery of carbon. A, okay. Oh, sorry. So this is recovery of elemental sulfur. So what is the typical reaction for this class process? Reaction. Class process reaction. Yes, I can understand that class process is the one that is used for recovery of elemental sulfur. That is what we discussed in the desulfurization process as well. So what is the reaction? Just a second. Okay. We have a H2S plus O2 gives SO2. Okay. And then that SO2 plus H2S gives sulfur. Just a second. Just a second. 1 minute. Okay. Oh, okay. So, yes, this is the cross process reaction. So, where H2S and O2 reacts to form SO2, and SO2 plus H2S gives sulfur. Okay. Now, next, let's move on towards this question, question 14. Identify the following process in the schematic diagram. So, just a second, let me make the schematic diagram big, a little bit bigger. So, I hope it is now clearly visible for all of you. So which process is it? B, plasma. Okay, one of you have told it's called plasma gasification process. So this plasma gasification process is some okay. The basic yes, this is the correct option, plasma gasification. So what you actually do is here you actually apply high voltage. So because of the high voltage, higher amount of energy, a plasma is created, and this plasma is basically at a temperature of up to 4000 degrees Celsius. So you can see how hot the plasma is, the fourth state of matter. So by using this electrode, you basically apply a high voltage, and because of that high voltage, a plasma is generated, and that plasma is basically at a high temperature of 4000 degrees Celsius, and this is going to be very well sufficient for burning of our carbon based feedstock. So based on this, if you see in case of the plasma gasification process, that gas that is going to get generated will be I mean, the feedstock you don't need to actually worry about. You're going to get a high quality syngas compared to what you got in the other three types of gasifiers, if you remember: fixed bed, fluidized bed, and entrained bed gasifier. You're basically going, in case of the plasma gasification process, the syngas quality is going to be extremely very high. Only the problem with this is it is a very new field. Still, a lot of research is going on based on this plasma gasification process on how to basically optimize the process and what are the merits and demerits of them. So, in case if you are interested, you are welcome to look at those research papers as well. But yes, for as far as this question is concerned, the answer is it's a plasma gasification process. So if you want basically a hint to identify how we can identify, it's basically based on this, the electric signals, so voltage signals. So basically, so this is the plasma gasification process. What about question this one? Identify the gasifier from the figure given in the side. So which type of gasifier this system is? Plasma entrained bed, or is it a double fluidized bed, or is it a circulating fluidized bed? Anyone? It's an entrained bed. Okay, somebody has told it's an entrained bed. It's an entrained bed gasifier. The biomass, steam, as well as the oxygen that you see is basically added from the top, and then it is burnt, and then you can basically obtain the syngas from the bottom of your gasifier. So the main thing is you need to actually know if this is for an entrained bed, then how does a, in case of a double fluidized bed, it is very easy to identify because you're actually going to use a combustor and a what do you say, combustor and a gasifier system, two different chambers for the gasification process. How do you identify the difference between entrained bed and a circulating fluidized bed gasifiers? Is there any difference in the way the architecture is, or their working operating system is better to say that word. Operating systems are oh, the circulating pipe is additional in CFPs. Okay. Okay, so just have a look at it for this one, and If you have anything to discuss, so the reason why I just rushed a little bit in the last two or three questions is basically because we have to solve one problem, and that's quite important. So if you have any doubts, you're welcome to let me know, or we have to solve one more question. We have approximately 20 minutes of time in our hand, and I hope that will be sufficient. So anyone with any quick questions, what we have discussed so far? Pyrolysis process we will discuss in the week 4 live interaction session. So all the problems or probably the MCQs that we were left out for today will be done in the next live interaction session. That will be the session on Sunday, day after tomorrow. Okay, so let's go to the question and let me show you the question. The question is as such what you can see. You have to develop an equation for the combustion of ethane. I hope all of you know the chemical formula for ethane. You have to develop an equation for the combustion of ethane with A, or that is going to be burnt A in theoretical air or theoretical or stoichiometric quantity of air, and 2 in 40 percentage of excess air, and determine the amount of air required for each gram of ethane that is getting burnt. So first is develop an equation for the combustion of ethane if it is burnt in theoretical requirement of air, and the second one is in case of excess of air, which is nothing but 40% in excess as per the question. Once you develop that equation, now you are supposed to calculate how much amount of the air will be required to burn 1 gram of ethane, and the empirical equation, chemical equation, is basically below. CXHY plus NO2 gives XCO2 plus YH2O. Again, you need to modify this equation a little bit, because here I have only this equation is framed only if you use oxygen, but the question says you are going to use air, so be careful. So try, give it a try for some time, and then let me start solving. So meanwhile, if you have any questions related to what we discussed on gasification, you can ask me now. So for, let's say, as a starting point, try to help me modify this equation based on the theoretical. So let me just give you a hint. First, okay, you can take your time to solve, and let's see. Let me start discussing after few minutes. So please, all of you, give it a try once for these kind of questions. Because for some of you, this question you may not be exactly familiar, so that is the reason I brought it for this particular live in for this for solving this question in today's session. So as such, if you see this course, there are few terms like, as we said, fixed bed, fluidized bed, and even in case of what we discussed today, like on gasifiers, you have some concepts like channeling, then you have something like blocking and stuff. So these are some terms in chemical engineering where we deal these terms greater in depth. So if you are a chemical engineer who is here today, or if you are a chemical engineering students who has some sort of an experience or probably learned about chemical reactors, you may be aware. But in case if you are not aware, or if you haven't, if you are not a if you are not in if your major is not in chemical engineering, so kindly have a look at these terms and try to have a basic understanding of what they actually mean, because as chemical engineers we deal with these concepts great in depth. So other branches, I'm not sure, they may or may not deal that as much as chemical engineers might do. So please have a look at at those if you are interested, because this course is on waste to energy conversion and we cannot devote more. I mean, it's only 2 hours live interaction session, so we cannot devote more time towards discussing on those concepts greater in detail. So that's the reason, if you are interested, you are welcome to please have a look at these terms in your free time. So, coming to the question, anyone with any idea on how to solve this, or how to basically reframe this equation? First is the reframing of the equation. This particular chemical equation that is given in the slide will not be useful for solving this question. You need to modify this, and then you can develop the first you can develop the equation, the combustion equation. Once that is done, once that is done correctly, you can calculate the amount of air required. Anyone who has modified this equation? Yes, no, anyone? So let me write this equation first. I'm going to directly copy this. CXHY plus NO2, sorry, gives X moles of CO2. Eh, Let me correct that. Plus Y moles of H2O. So now I am supposed to modify this equation, and when I mean modification, this equation is particularly for the combustion of any kind of a hydrocarbon in the presence of oxygen. But here, my fuel, or you can say my oxidant, is not just going to be only O2, it's also, it is actually air. So, in air as such, if you see, it's not just that only oxygen is present, as all of you know, you have a significant fraction of nitrogen. So, you need to modify this equation by considering the presence of nitrogen as well in the air. So, if you modify this, it would be somewhere, it would be typically, it should look like just a second. Plus N2, because your nitrogen is going to remain inert, they are not going to react with your hydrocarbons by any chance. So that nitrogen gas will be present in your system as such. So it will be there in the product gas that you get as such as nitrogen itself. So now you need to write a balanced chemical equation. So either you can substitute the hydrocarbon as ethane and then develop the equation, or you can write a general equation and then you can use it for any kind of hydrocarbon. It is totally your wish. So here now, for the time being, I'm going to write it for a general hydrocarbon. So the first question that I have to assume is, or that I have to basically tackle is, what is the value of, I mean, can I use O2 and N2 in 1 is to 1 ratio? Can I, is the way of me representing air is correct? Chemically speaking, whether my representation in this particular equation is correct for the, for air. Because as you know, air contains 79 percentage of nitrogen, N2, and 21 percentage of oxygen. The other gases which are going to contribute, we are neglecting it, because those percentage will be very minimal. All these all the other gases put together, if you see, they will be contributing to less than 1%. So for this particular question, we are basically neglecting the contribution from other gases. The only two things that we are going to consider here for our particular question is the nitrogen gas and oxygen gas. Now my question is it that for, like, for every 1 mole of O2 that is present in air, do you have 1 mole of nitrogen, or is that fraction, or is that number going to be different? So for every 1 mole of nitrogen in air, do you have 1 mole of oxygen, or is the value going to be something else? Anyone? Oh, we have somebody. Okay, but I think Lakshmi ma'am, I think you have written this equation by considering only oxygen in the air. So if you see the question, it's not just only for oxygen. I am asking for air. So air as a whole. It's not just only for oxygen. So let me just write this particular part. I hope with that all of you may be able to. Air has 79% of nitrogen and 21 percentage of oxygen. Yes, so for every 1 mole of air you have 79 percentage nitrogen and 21 percentage oxygen. So does that mean, so what can I write with this? So can I write for 1 mole of O2 I have 79 by 21 moles of N2. So in air, for every for 79 percentage is going to be nitrogen and 21 percentage is going to be oxygen. So let me take the basis for air as 100 moles. So because I want to make the calculations easy, let me take it as 100 moles. So for every 100 mole of air, 79 moles is going to be in nitrogen N2 and 21 moles is going to be your oxygen O2. So with this relation, can I say for every 1 mole of O2 in air, there is approximately 79 by 21 moles of nitrogen gas N2. Is my statement valid? Oh, we have some. Okay. So you can write like I hope all of you are clear. If you have doubts, please let me know. So 79 by 21 is 3.76 if I am not wrong. Calculator. 79 by 21. 3.76 mole of N2. I'll write here basis. I'm considering. You can consider 1 mole and then you can write it as 0.79 by 0.21. It's going to come out as the same. So basis I'm considering here as 100 moles of air. Is this way of writing is fine? Oh, oh, sorry. Some problem. Anyway, leave it. I'll just write it once again. So can I write it as CXHY plus N times oxygen plus 3.76 3.76 nitrogen gas gives XCO2 plus YH2O plus 3.76 N2. Just let me correct this. Is this correct? Because since nitrogen is not going to react with your hydrocarbon, that many moles of nitrogen that is entering inside the system or burning with the hydrocarbon is going to be emitted out as a product gas. Is this correct? If you see the number of moles on the reactant and the product side, should be equal for law of conservation of mass or moles. So is this fine? Now once you know this particular equation, it's just that you need to substitute for ethane what it will be. So with that, for a theoretical air requirement or theoretical air that is basically getting supplied, this is the combustion equation for ethane. Can I write it that way? So as somebody said, ethane is C2H6. Of course, that's the chemical formula, plus N times. Let me balance the chemical equation once I completely write it down. Gives, so can I just copy paste this one here? Oh, so with this is the chemical equation. So I just now need to basically make sure that everything is balanced. So for two carbons on the reactant side, you will have two here on the product, and here you will have six hydrogens, so three. So if you see, the amount of oxygen will be 7. 2 times 2 4, 4 plus 3 7. So this will be 3.5, yeah. So 3.5 times 3.76. Here the value of n will be 3.5. So now you need to multiply this. Let me copy this again. So 3.76 times 3.5 is 13.16. So this value is going to be 13.16 moles of N2. Now this is the combustion equation of ethane with the theoretical air requirement. Now we know this balanced chemical equation. For now, what we just want to know is, if you are going to use 1 gram of ethane, how many grams of air is required. So I think that is basically only the moles that you're, I mean, molecular, based on the molecular weight, you need to calculate that. So can you just let me know how much amount of air is required? Molecular weight of C2H6 is 30 gram per mole. Now, for every 1 mole of C2H6, you have 3.5 moles of oxygen plus 3.76 moles of nitrogen, or you can say 13.76 as total. air, this one. So now you just need to calculate, I mean do the math. So please let me know what will be the answer. So that means, so what will be the molecular, what will be the weight of 3.5 moles of O2 plus N2? I mean oxygen gas plus 3.76 moles of nitrogen gas. So oxygen will be 32, 3.76 times N2 will be 28. So what is that value? 105.28 plus 32, 137.28 times 3.5, 480.48. Is that right? Oh, somebody is getting 372.19. Let me just recheck my calculation. 3.76 times 28 plus 32, okay, times 3.5. Uh, can you please recheck your calculations? May I know who's that? Oh, Lakshmi ma'am, please recheck your calculations because I'm getting 480.48 grams for 3.5 mole of air. So kindly check your calculations once again, and if you have any difficulty, let me know. So what it typically means is for 30 grams of, let me just do one. So for 30 grams of C2H6, 480.48 grams of air is required. So for 1 gram of ethane, how much air will be required? Simple, it's just division. So 480.48 by 30, 16.016, or you can say 16.01 grams of air is required. Now, what will be the difference in the value if I'm going to say that this particular combustion is happening in oxygen environment, not in air? So then, if that is the equation, then as somebody rightly said, C2H6 plus 3.5 times of O2. So then if you do that calculation, then it would be somewhere around, if I am not wrong, 30 by 32 is 16 by 15. 1 point, somewhere around 4 grams of air, if I am not wrong. 4 grams of oxygen. So if, let me just check. 3.5 times 32 by 30. 3.733 grams of oxygen will be required. O2 will be used for combustion of ethane. So if you have any questions, then please let me know. Anyone with any questions, any doubts in the overall process of how we solve this particular problem? I know that we are actually going past our time, and I'm taking up some of your dinner time. So please let me know about this. Then once if you have clarity with this, then the x 40 percentage of excess of air will be a kind of, a practice question. You can take it up during the week, or probably within the 2 days time that is available for you, and then you can let me know this answer in the next session. Over there, it's a everything will remain simple except for the fact that you need to consider that 40 percentage excess of air. So you just need to multiply it with a particular factor, then you will be able to find out the answer for that. So it's not a big deal unless you entirely solve the problem. It's just about a small modification that you need to do to the answer. So anyone with any questions or any queries related to what we discussed so far? Whatever we discussed in today's or any of this live interaction session that we have had. Again, as a practice, you can also take up for different kinds of hydrocarbon and kind of like know how much amount of air will be required depending upon how the increase in the carbon chain, how the increase in the carbon chain basically makes a difference in the air required for their combustion. So you can take it as up as an kind of a task, and then you can try seeing the relationship of how adding every methyl to that hydrocarbon chain affects how much amount of air will be required. And you can do the math, and you can, if you want, you can also see that for 1 gram of air how much amount of money is basically used, and based on that you can do some sort of uh, you can say a techno-economic calculations, and then see the difference as well. So if you do not have any questions, then I think we can. Oh, uh, 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 22.4224. Oh, okay, for 40 percentage of excess of air. Let me just check it once. Just a second. Yeah, the answer is right. It's 22.4224. So then, okay. So with that, let me just stop sharing. I'll post one question in the chat box. So the question is, uh, so the question is, how much amount of excess of nitrogen will be obtained in the product side if we use 40 percentage of excess of air compared to the theoretical air requirement? So kindly calculate this as well, and then let's see in the next is live interaction session. So again, if you have any doubts, you are welcome to ask me, or if you have any case of feedback that you would like to share it with me about the live interaction session, then you are also welcome to do it now. Any suggestions, any queries, any feedback from anyone? Okay, so in case if you have no queries for the time being, then I think we can conclude our session for today. So you can post your queries in the Q&A section. I will see to that it gets answered. So yeah, let me conclude the session for today. Thank you all for joining today's live interaction session. Our next live interaction session will be on 15th of February from 5 p.m. to 7 p.m. on Sunday. So that will be the fourth live interaction session. So I hope to meet you all there. Uh, I thank I take this as an opportunity to thank Professor Prasenjit Mondal sir as well as the NPTEL team for providing me this opportunity to interact with you all in this evening. So thank you all for joining today's live interaction session, and I hope all of you to meet on 15th of February. Till then, thank you and have a wonderful weekend ahead. Thank you and bye.